Okay, I think we're ready. All right, so if you were unfortunate enough to go on Moodle last night, you might have seen just a complete mess of things on there. Don't worry about that. It should be hidden now. So how do I change it to switch role to students? So it should look like this now, or something like this. I don't know about the side panel, but so what I did was we're going to be using a free resource because we're trying to keep it free here. But it took me a long time to kind of figure out how it works. So I finally was able to bring in everything, and that was tricky. So now it's in. So one thing that I will say is that it is linked, so it should be linked to something called MyOpenMath. You don't need to have an account, and that's why I linked it. But just so you know, it will be transporting your grades into Moodle. So it should. So what's nice is that the grades should get transferred automatically from MyOpenMath into Moodle, but that means that it has access to your student number and your name. So if you're concerned about that, then please just let me know, and I can link them some other way. But it's just nice to have them kind of update automatically. Okay, so we've got our fundamentals part 2 that we're going to work through this week. Hopefully we'll get through all of it. Typically I don't get through 1.3 takes a long time, so we'll see where we get to today. But we'll finish up the fundamentals from last week. We had just a little bit left. And then we've got this new section of, the namings are, I'll revamp it a little bit, but there's a resource here called Online Graphing Calculators. And so there are a lot of options that we can use. I'll show you guys how to use Desmos when the time comes. So we will be using Desmos a little bit for graphing and just to kind of see how things behave. But there are a lot of different options. So that's good. And you should have this intro to MyOpenMath quiz on here. It's not all counted as an assignment, but it's really just a way for you to get familiar with how to enter answers and things like that. So I'm hoping that when you click on it, okay. Well, this might be an iPad thing, but I'm hoping once you go in, it should take you to a different page with a quiz. So I'll leave that for now. And then there's another, and then there's the intermediate algebra diagnostic. Oh, awesome. Okay, so it must be an iPad blocking thing. So that's great. So it takes you to a little quiz. I'll count it as an assignment, but it's really just kind of, do you know how to enter things into MyOpenMath? Because it'll require you to enter things in a specific way. So, and then the intermediate algebra diagnostic, we're working through all those fundamentals, so maybe hold off. I made these both due next Thursday, I think. It should say on there. But I can adjust the date depending on how long it takes us. So, so don't worry about that, but I just wanted to show you where it is. So let me go to our notes, and because there are a couple of fun things going on with MyOpenMath. Oh, October 1st, which is, yeah, next Thursday. Okay, cool. That's good. Like I said, we'll see where we get to, and then I might adjust it depending on how far we get. Okay. There are 2 MyOpenMath assignments hosted on Moodle. I'll say both due October 1st, right? But I'll say may change depending on material covered this week. Right, if I feel like you need more time, then that's good. It might be fun to give it a go, okay? But I'll talk about attempts and penalties in a little bit here. It may change depending on material covered this week. Okay. So, one fun thing about MyOpenMath is you get 2 late passes, or I've given you 2 late passes. So you get 2 late passes. 2 late passes. Okay. What a late pass does is it extends the due date by 24 hours. Okay. So it extends the due date. Due date. I always do that. I combine 2 words. Due date by 24 hours. Okay. But it has to be applied before the assignment is due. Okay, so I'm going to do that in pink because that's really important. LP, so the late pass must be applied before the assignment is due, right? Once started, is there a time limit or limit on going back to finish? No. So for these assignments, you can kind of take however long you want. You can go back, you can open it back up, you can shut it down, and it should save your results. You know, it is a free resource, so it does have, you know, some glitches and stuff, but I've used it before and for stats, and so this one's a little bit different, but it worked pretty well. So if there are any issues, then just let me know. But yeah, so you should be able to open it, close it, come back. But as far as your attempts go, okay, so I've said it, you have 10 attempts per question, but so your first 2 are freebies, and then after that, your 3rd attempt, your 4th attempt, each of those are gonna be penalized by 5%, right? So it just deducts 5% for each, which isn't that bad, right? But so each question has 10 attempts. Okay. But minus 5% after 2 attempts. Okay, so that's important for you guys to know, but also if that's not how it's behaving, then you need to let me know, because that's how it should be behaving. So if you're finding that that's not what it's doing, then just let me know kind of ASAP. Okay, cool. So have a poke around there, right? You've got time to do those, but maybe try that intro to MyOpenMath just to kind of see how to enter answers and stuff and see how it goes. Okay. Any other question? I'm keeping an eye on the chat here, but I don't see any other questions. So that's good. So, okay, so I'll leave that with you guys. Check it out. See how you like it. We don't have any options, so we're gonna use it, but just kind of get familiar with it. We'll do a little bit of review, not so much covering material, but just talking about, just so we can refresh our memory about what we did last day, because it was a long time ago. We talked about intervals, right? Interval notation, drawing it on the line, and set notation that goes with it, right? We talked about intervals, inequalities. Yeah, so it's minus 5%. So your third attempt, even if you get it right, you get minus 5% on the question, just because you know, it took you 3 attempts to get there. But your first 2 attempts should be free, right? So if you get it right on your second attempt, then you're good. And so hopefully it's behaving that way. So we talked about intervals and inequalities. And inequalities, right? Less than, greater than, all that fun stuff. We talked about absolute values. We talked about the absolute value properties, but also how we use the absolute value to find the distance between 2 points. Right? So we talked about absolute values, their properties, the distance between 2 points, and then we got into exponents. Exponents, so we had to talk about the laws of exponents. There's a lot of laws of exponents that I expect you to be fluent in, right? And so we talked about the laws of exponents. Scientific notation, right, kind of comes with exponents. Scientific notation. And then we finished off by talking about the nth root, right? So we're used to the square root, but now we're talking about the nth root. So we said if I have to take the nth root of a, for example, on your calculator, right, there is no nth root button. That's okay, because what we do is we do a to the power of 1 over n, right? Making sure that this 1 over n is all in the power, right? If you don't have a screen where it shows you what's in the power, then you'll want to make sure that you put brackets around the 1 over n just to make sure that it's all in the exponent. So we'll keep talking about the nth root and how we use it and how it behaves now. Okay. Keeping an eye on the chat, but I think we're doing okay. But if you have any questions, just throw them in the chat. Okay. So, where were we? Okay, here. So the nth root, we use it to undo the nth power. So the nth root is used to, I'll put undo, right? Just like multiplying undoes division, adding undoes subtraction. So we've got these kind of links between these operations, right? So the nth root is used to undo the nth power. Okay. So what I mean by that is, well, if I have a to the power of n, right, and then I take the nth root of that, all I'm left with is, so let's try to write this out, right? We've got a to the power of n to the power of 1 over n, right? Because I can rewrite that nth root as to the power of 1 over n. But now, because I know how exponents behave, right? From last day, we talked about the laws of exponents. And so these exponents, I can rewrite as a to the power of n times 1 over n. N times 1 over n, if you think about it, n can be rewritten as n over 1, right? So now I'm just talking about multiplying fractions, right? So now I've got a to the power of n over n. A to the power of n over n is just 1. Which is just a, right? So that's what I mean by the nth root undoes the nth power. So for example, if I have a to the power of 3, right, and I take the third root, well, I know I just get a, right? So you don't need to show all this here. That's just a fact. Okay? So let's talk about the properties of the nth roots. What's the date today? 20th? Yeah, it is the 22nd. Crazy, time flies. So we've got these properties of the nth roots. Because the nth root is just an exponent, right? It makes sense that we can break it up as long as we're multiplying inside, right? So that should be, as long as you rewrite it as a times b to the power of 1 over n, or all to the power of 1 over n, then this splitting, right, should make sense. Okay? Same thing with the nth root of a over b. So if you've got division in there, then you can break it up just because you are basically dealing with an exponent, right? Even the nth root of the nth root of a, we can simplify as just the m times nth root of a. Okay? So let's have a look at, we look at 3. If I've got the mth root, here we go. Start with the nth root of a and then take the mth root of that. Okay. Just rewriting things in terms of exponents. I'm going to rewrite from the outside in, but you could easily just do it from the inside out. Doesn't matter. So I've got the nth root of a to the power of 1 over m. Okay. That's the same thing. But what if I take the inside and I rewrite it as a to the 1 over n to the power of 1 over m? Well, because I've got these exponents, I can multiply them. So I get a to the power of 1 over n times m. Well, that's the nth root of a. Okay. So that's where that came from. Okay. Here's what we just talked about, right? One kind of sneaky thing is, so we established it just assuming that n is odd. So the nth root of a to the power of n is a if n is odd. Okay? And if you take the nth root of a to the power of n, it's the absolute value of n if n is even. Okay, so you're always going to get a positive number. Or, yeah, if n is even. Okay. I'll add that in here. No, it's okay. We're good. We're good. Okay, so what did I want to do? Oh yeah, let's do an example using these laws. So if I want to simplify the third root of a squared b times the third root of 64a to the fourth b. So we want to simplify this, so ideally we want to get them kind of merged together, and because we're multiplying here, right, we can split things up and we can kind of, it'll act like an accordion and kind of do whatever we want it to do. So if you had to simplify this, right, I'm looking at an a here and an a here, a b here and a b here. I've got the third root. So surely there are things that we can do here to kind of smush things together. So let's see here. Where do we want to start? Well, one thing we can start with is we can rewrite this all under the third root, right? Because from this property here, this first property, right, basically what I've got going on is the right-hand side, right, and I want to move it to the left-hand side so it's all under the same third root. So I can do that, the third root, but what I'm going to do is I'm just going to highlight what items came from where with these brackets. So I'm going to have a squared times b times 64a to the fourth times b. So this, right, now I can simplify on the inside, and then hopefully later on I can split this up and kind of simplify the root as well. But I'm going to just leave the third root as it is. And I've got 64 times a to the power, so I've got a squared times a to the fourth. I know I can just add those exponents, right? So I've got a to the sixth, so I am skipping a couple of steps now, right? We're working a little bit faster than we have been. So b times b is b squared, right? B to the 1 times b to the 1 is b to the 1 plus 1, b squared. Okay, so if we've got 64 in there, right, I'd be tempted to see if it becomes just a nice whole number. Otherwise, I would leave it as the third root of 64. In fact, now I can kind of, like I said, I can do whatever I want with this thing. I can kind of treat it like an accordion. So I can smush the roots together. I can pull them apart. I'm allowed to do that because I'm multiplying inside, right? Only multiplying. So I can rewrite this as the third root of 64 times the third root of a to the sixth times the third root of b squared. So remember, right, to check this on your calculator, the third root of 64 is 64 to the power of 1 over 3. So let's try it. 64 to the power of 1 over 3 gives me a nice 4, right? So I'd way rather be dealing with that. So that's what I'm going to swap out here. Equals 4. And then I've got times a to the 6th to the 1 over 3. And then just from experience, I can tell that that b squared, the third root of b squared, isn't going to go anywhere. So I'm just going to leave it. But what looks promising is the 6 divided by 3, right, is going to give me a nicer power of a, right? And so I get times the third root of b squared. And you could rewrite it if you wanted, but 4 times a to the power of 6 divided by 3, 4a squared times the third root of b squared. So that's the simplified version. So let's grab we've already kind of seen it, so okay. We've already seen this, right? But here it is explicitly. So if we have an exponent of m over n, right, we saw that we can rewrite that as the nth root of a to the power of m, right? Or if we wanted to, just the nth root of and have the power of m inside the root, it really doesn't matter, right? The m is on top, right? So the m is in the numerator in the exponent, and so it's going to stick with the a, right? And the over n, so the n is in the denominator of the exponent, and so it's going to be the nth root, right? These two are equivalent statements. Okay? So here, one thing to note is that for even roots, we can only take the root, so the even root of a positive number. Okay. We can only take the even root of a positive number. So that's for even roots. Odd roots are fine. We can take the odd root. We can take the third root of -2, for example. But if you try to do, let's see here, if you do negative, so if you do the square root, that's an even root of -2, for example, it should just give you a math error of some sort, right? And so that's a good reminder that, okay, just like we can't divide by 0, another thing to lock in is that we can't take the even root of a positive number. Right? So these are rules that are going to come into play later, especially when we're dealing with the domain of a function. But good to kind of start locking in now. Okay, so how about another example? So again, we're just going to simplify and we don't want to have any negative exponents here, so and eliminate negative exponents. For it's all under the square root of 16 u to the 3v over u to the v, or times v to the 5th. So we want to simplify this thing, and again, just kind of surveying the scene. Okay, I can take the square root of 16, that sounds familiar, right? U to the 3 and u and v to the 1 and v to the 5th. Right? I should be able to simplify those quite a bit. So what I'm going to do, and there are a few ways that we could go about it, right? I could split up, because I'm only multiplying and dividing in here, I'm allowed to split this square root kind of open onto each individual item. But I think it's going to be easier to deal with this one by simplifying the inside and then distributing the square root and seeing where it gets us. So if I have So I'm going to keep the square root. Oops. So when people kind of get started with this type of math and we get to bigger equations, I know people are tempted to maybe not draw the square root because for some reason it's too tedious. And there will be things that you should be keeping all along, and it will feel tedious, and it is. But you should always just write everything out, every step, and even if it's not changing. So we've got 16 u to the 3b. Now we can use everything we know about exponents, right? Negative exponents, we can move it up to the numerator. So now I've got u to the -1 times v to the -5. And I'm going to make this a square root just on that same line, right? Because now I can simplify in here and kind of see what falls out. So I've got the square root of 16. U to the 3 times u to the -1 is u to the, and I'll show it, but you could just go u to the 2 if you wanted to. U to the 3 plus -1, and then v to the 1 plus -5 is, I'll do another line here, is the 16th root of u to the 2 and v, oops, to the -4. 1 minus 5 is -4. Okay, so to simplify this even more, right, because I'm multiplying in here, it doesn't work if you're adding or subtracting it. It really doesn't work. But because I'm multiplying in here, I'm allowed to distribute the square root to see where it gets me. So I've got the square root of 16 times, oops, what happened here? Hey. There. The square root of 16 times the square root of u squared times the square root of v to the -4. So the square root of 16, fair enough, you can use your calculator. It's just the square root, so now we have that square root button, but you might remember that it's 4. Here, right, I could go through and I could write, okay, u squared times 1/2, that's u to the 2 over 2, u to the 1, but I want us to get comfortable with just rewriting this as just u, right? And then v to the -4 and then the square root, that's the same as v to the -4 divided by 2. So that one maybe I will write out v to the -4 divided by 2. Well, that's going to be v to the -2, right? But I wanted to eliminate negative exponents, right? So here I am. I've got 4u v to the -2, but to eliminate that negative exponent, I'm going to have to put the v squared down in the numerator, or sorry, in the denominator. So I've got 4u over v squared. So notice how all the things that we've talked about so far are really just kind of getting baked in, right? Dealing with exponents, dealing with fractions, right? So they're all fundamentals, right? And that's why we're spending so much time on it, because it'll serve us well. Okay. I haven't seen any questions pop up, so I'm just gonna keep going. Okay, so we're going to talk about something called rationalizing the denominator and also putting things into standard form. So there will be a couple of different standard forms that come up, but this is the first one that we'll see. Okay? This is going to be more, you'll use this if you go into calculus, but it's just one of those things that it's just good to know that we can do it. Rationalize the denominator. We could also rationalize the numerator, but it's more common to rationalize the denominator. So what does that mean? It means, I'll cut this whole section here. Put it in here. Hey, didn't copy. Copy. Paste. Whee. Okay. So the root, so when I say a radical, right, so to eliminate a radical in the denominator is just eliminating a root. So a radical is a root. Okay, and it doesn't have to be the square root, it can be the nth root, which we'll see in a little bit here. And so if we want to rationalize the denominator, what we're saying is that we've got a root in the denominator, right, that we want to morph into not a radical, right? So not a root anymore. It does come at the expense of having a root in the numerator, but maybe that's easier to deal with, right? And so what we do is we multiply by 1, right? So again, we're seeing this convenient value of 1. Right, and so what we do is we say, okay, well, if I've got a root a here in the denominator, right, and I don't want to have a root in the denominator, all I'm going to do is I'm going to multiply by root a over root a, and we know that the root of a times the root of a is a to the 1/2 times a to the 1/2. A to the 1/2 plus 1/2 is a to the 1. And so now all of a sudden we're just at a in the denominator, right? But we're left with this 1 times root a in the numerator. And that's kind of the price that we pay. So let's see here. Do I have a little, let me just go back here and see if I have, where did I go? Okay. I found a little example. Let's do, put into standard form, have a good day. Put into standard form by rationalizing the denominator. Okay. So first we'll start with 1 over root 6. And then I want to do 12 over root 3. Hey, where'd it go? There we go. Okay, we're back. Kind of put this off to the side for a little bit. We'll do 1 over root 6 first. So putting it into standard form just means Where does it say? Oh, I guess I never said in here. I'm just looking for where it says the standard form. But anyways, this is the standard form where you don't have a root in the denominator. I think it says later, so that's why I'm not gonna worry about it too much. But okay, so we're gonna rationalize the denominator. So I've got 1 over root 6. So what I have to do is, well, I've got 1 over root 6, and then remember we multiply by 1, and because I want to undo that root 6 and I don't want to have a root down there anymore, the easiest thing to do is just times root 6 over root 6. Right? Root 6 times root 6 is just going to give me 6. Right? And you can do it. You can rewrite it as exponents, right? 6 to the power of 1/2 times 6 to the power of 1/2. I'm multiplying fractions here, right? So everything that we've seen so far, it's all coming into play, right? And so I'm expecting you to be pretty comfortable with that now. So I've got root 6 over 6. There we go. Now it's in standard form because I've rationalized the denominator. Let's do 12 over root 3. Same idea. I don't want that root 3 in the denominator. I'm okay with having a root in the numerator, but I really don't want to have it in the denominator. So I've got 12 over root 3. And then to ditch that root 3, I'm going to do times root 3 over root 3. So then I've got 12 root 3, that's fine. It's in the numerator, so it's easier. Over 3, because I'm multiplying here, right? I'm allowed to cancel this 3. Why do I say because I'm multiplying? Well, because if I had 12 plus root 3, I wouldn't be able to cancel this 3. I would have to be able to pull out a common 3 from each of these, which I wouldn't have if it was 12 plus root 3. So, but because I'm multiplying here, I can do 12 divided by 3, which puts me just at 4 times root 3. Right? So what I'll do is 12 divided by 3 equals 4. Good. We don't have to limit ourselves to square roots. In fact, usually we won't just have square roots to deal with, but the same kind of logic applies, right? And so if we go back and steal this little blurb, so now we're saying, okay, in general, if the denominator is the nth root of a to the power of m, just allowing for not just a's in there, but a to the power of m. So then as long as m is less than n, the reason for that is if m is greater than n, we'll be able to cancel before we have to deal with it. But anyways, we'll just have m is less than n. Then we multiply the numerator and denominator, so our convenient value of 1 is going to be the nth root of a to the n minus m, right? So here, what this is saying is our convenient value of 1, and maybe I'll put it down here, of 1 is going to be the nth root of a to the n minus m over the nth root of a to the n minus m. And here, this is the reason why, right? So if I have the nth root of a to the m times the nth root of a to the n minus m, I can combine these so that they're all under the nth root, right? And then I have the same base, a, which means that I can add these exponents, so a to the m plus n minus m, m plus n minus m puts me at just n, right? So now I've got the nth root of a to the n, which we know is a. Right? So here, a fractional expression whose denominator contains no radicals, so no roots, is said to be in standard form. I knew I had it. The denominator contains no radicals, so no roots, is said to be in standard form. Okay, so if you're asked to put things into standard form, it just means no roots in the denominator. In fact, I'll write it here. So standard form, just kind of shorthand, means no roots in the denominator. Okay. So if we do a little example, if I get you to put a over the 6th root of b squared into standard form. So I want you to use this that we just talked about to put it into standard form, right? Remembering that our convenient value of 1 is going to be the nth root of a to the n minus m. In fact, I'll extend this so it looks proper. Sloppy. So I'll let you give that a quick go on your own. And we'll write it, I'll start setting it up here. A over the 6th root, b squared. So first thing I'm going to do is I'm going to highlight what my n is and what my m is, because here I see that I've got some nth root and some m-th power inside that root, right? So what I'm going to do here is I'm going to say, okay, well, in this case, n is 6, right? If I'm trying to match this notation here, right, or here, it's all the same, right? So n is 6 and m would be 2. So what I'm going to have to do is I'm going to say, and it's not obvious without more practice, right? It's not going to be obvious that our convenient value of 1 is the nth root of a to the n minus m. So it's not until you've practiced it that it's going to come kind of more naturally. But what we're going to do is we're going to have a over the 6th root of b squared, and then times the 6th root of b, right? It's not a anymore, right? This is what I'm trying to rationalize, right? And so I've got b squared. Well, I have to write that as b to the power of n minus m. In this case, I've got 6 minus 2. And then because I need this to equal 1, right, I just have the same thing in the denominator. So the 6th root of b to the 6 minus 2. Okay. So what I get is, because I'm multiplying these, right, I've got a times the 6th root of b to the power of 4 over, and because I'm multiplying in the denominator as well, I've got the 6th root and the 6th root being multiplied, so I can smush these together. And so what I get is I get the 6th root of b to the power of 2. Can I skip a step? No, I guess not. B to the 6 minus 2. I will eventually just skip to b to the power of 6 eventually, but 2 plus 6 minus 2. But here I'm still showing you all the steps, right? But if you wanted to skip straight there, that's fine. So I've got a times the 6th root of b to the 4, which I guess I could simplify, but it's just going to be b to the 4 over 6, which is what I'm thinking I could simplify, but I'm just going to leave it, because the goal is to get it into standard form, meaning I don't want to have a root in the denominator. And then if it makes the numerator look nice, then that's fine, but it's not a must. So then I have the 6th root of b to the power of 2 plus 6 minus 2. Putting me at a to the times 6, the 6th root of b to the 4th over the 6th root of b to the 6th. Well, here I'm just going to show you how I kind of think about it, right? So the 6th root of b to the power of 6, I know just gives me b, right? So I just kind of think of it as canceling. Okay. So then I get a times the 6th root of b to the 4 over b. And now it's in standard form. In standard form, since there are no roots in the denominator, no. Okay. So a little bit more challenging. Not hard, as long as you kind of have the formula to use in front of you. But you could even play around with it, as long as you remember that the whole goal is to get rid of the roots in the denominator, and you just got to do what you got to do to get there, right? All right. So that's the end of 1.2. Notice these are huge sections. Later on, the sections won't be this huge, but there's a lot of material in here, right? And so, and like I said, 1.3 could take us a little while. We'll see how we do. I think in my notes I have that it definitely took a whole day, and now we've kind of spent half a day on 1.2, so we'll see. So 1.3 is on algebraic expressions. We'll start by talking about polynomials. Later on, we'll talk more about polynomials, but for now, we just want to talk about their general layout. And you might remember polynomials from high school or some other math course. They're very common. So let's start. So this is in your fundamentals part 2, and for some reason the print when I put it together, the font is just huge. But anyways, because I was just working on the one page, it looked normal, and then when I put them side by side to the other sections, it's huge. But anyways. Okay, oh, that's the one I wanted to grab. So we'll start by talking about polynomials. Okay. So a polynomial is just anything with multiple variables of x, so multiple different powers of x all combined, and they can have some coefficient, right? So each x, right, with its power is going to have its own coefficient. So here, this is a coefficient. Actually, I should keep it clean up there. So if we have a to the subscript n, so an times x to the n plus an minus 1, so the n minus 1 subscript is just a little notation that we use to say that it's not necessarily the same as a to the n or an. It's a new thing, an minus 1. I'll show you an example with numbers in just a little bit. Plus a1x plus a0. Okay. So these are what we call coefficients. Okay. This whole thing is a term. Okay. And the highest power, I don't know which color can I use here. Highest power of x is the degree of the polynomial. So we've got this kind of I don't know, assumption. So if a subscript n is not equal to 0, so let's just think about what would happen if an was 0. Well, then if an is 0, then you've got 0 times x to the highest power. But then, so then this term would go away, right? So there are instances where these coefficients might be 0, which means they're just gone out of the equation. So we're allowed to have these coefficients of 0, but this here, if an is not equal to 0, well, it means that this term exists, and that's what makes it the highest power of x. So I kind of skipped that part, but whatever the highest power of x is, that's the degree of your polynomial. Okay. So for example, a polynomial might look like 4x squared plus 3x. Right? Here's a polynomial. Yeah. Technically, what you've got, right? So here, x squared, so the degree of this polynomial is 2. And you've got, so 4x squared plus 3x, and then technically what you have is plus 0, right? 0 times x to the power of 0, technically, right? Because here you've got 3x to the power of 1, and so the whole idea of a polynomial is that, okay, if you've got a degree 2, then you start at 2, and then there are powers of x decreasing from 2, right? But here, just x is technically x to the power of 1. And then if there's no term after, then what's technically going on is you've got 0 times x to the power of 0. Here, I want to make a note that because this is going to be important, anything to the power of 0 is just 1, right? and it should let you do it. So 3 to the power of 0 is just 1 on your calculator. Here. Anything to the power of 0. I'm sure we've said it when we were dealing with exponents, but now it's really going to come into play, and so that's why I want to highlight it. So anything to the power of 0 is 1, or is equal to 1. So 0 times 1 is 0, so that's why it's gone. Okay. So we can't just talk about polynomials, we have to work with polynomials. And so let's get into kind of adding and subtracting polynomials. So adding and subtracting polynomials, you always want to collect like terms, right? So remember, you're dealing with powers, so exponents, and we know how to deal with exponents now. And so if we've got something like 5x to the 7 plus 3x to the 7, well, if I've got x to the 7 and x to the 7, what I can do is I can pull out that common x to the 7 and then have the 5 plus 3 in front as my new coefficient, and then x to the 7 putting me at 8x to the 7, right? So here I'm just gonna combine like terms, right, or pull out, maybe I should write it on this one instead. Pull out the common x to the 7. And then we can deal with the coefficients, right? So to simplify a polynomial, right, if you have x to the 4th 3 times over, then you can simplify that by combining the coefficients. Right? So pull out the common x to the 7 and combine the coefficients. So obviously it's all in red and everything like that, but just make sure that you pay attention, right? Because we've talked about the distributive property, right? And so here, if you've got a minus in front, then of parentheses, then you have to bring that minus inside, right? When you break up or expand the parentheses. So then if you've got negative b plus c, well, that's the same as negative b minus c. Okay. And so that's going to be important. We'll do a couple of examples here, or at least just one maybe. So yeah, 1.3 is where I started just incorporating a bunch of different practice problems. Some of these are a little bit, well, not at this point. So you should be able to do all of these. And I'll see if I can get the solutions put together. I might have them already, so that would be good. Otherwise, yeah, we'll see. But I'll check for the solutions. In fact, let me write it out. Check for question solutions. I feel like I have them somewhere, but where? Okay, so we'll pick one of these, right? But just make sure that you get comfortable working through these, right? So you've got lots to choose from here, just for extra practice. Let's do 22. Oh, I'm on the wrong page, aren't I? I meant to just come grab this here. That's what I wanted to do. So 22, let's do that one. Looks as good as any. So what we're going to do is we want to just find the sum, the difference, or the product of this polynomial. So we just want to get comfortable working with polynomials and just kind of expanding things and simplifying things until we have a nice looking polynomial. So if we've got 4 times x squared minus 3x plus 5 minus 3 times x squared minus 2x plus 1. So if I just want to simplify this, right, we're doing my favorite is expanding, right, expanding and simplifying. And so we're going to use the distributive property, right, to bring this 4 inside, being careful with the -3 as we bring it inside, right, has to be brought into all of these terms. So if we take a step back, I've got a polynomial here and a polynomial here, right? So I've got 2 polynomials being, well, subtracted. But I can reduce this or simplify this to 1 polynomial, right? So because it's pretty wide, right, I'm going to start my, my equal sign down below. I'm not going to try to squeeze it in here because remember, I want to try to stack my equal signs. And so if I'm trying to stack them on this side, I'm just going to constantly not have any room. So that's why I'm putting it over here. Okay. So first things first. Nice. That's right. So let's see if we can get there. So we have to expand the 4 inside. So I've got 4x squared. I don't know, are you guys okay with me just doing the 3 times 4 right away? Or maybe I should show it. Minus 4 times 3x plus 4 times 5. I'm going to keep brackets around here, even though I've kind of expanded them away, but just to show that, okay, that's that lump of stuff that I've dealt with. Now I'm moving on to the -3. So then I've got minus 3 times x squared. Now here's where I need to be careful, right? I've got minus -3 times 2 because the -2, so there are a couple of different options. You could keep the negative on the 2 and just have a plus here. I broke it up. Maybe I'll do 2x. And then plus -3 times 1. So lots of different ways you could show it. Weird. So dark. I need to come closer. Okay. So then, oh, no bracket here. Actually, you know what? I'm going to rewrite this as plus -3, just to have the same kind of setup. And then I'll round these off with brackets just to show that which terms are which and which polynomials come from where. So now I've got, okay, so now I can just go through and kind of simplify things. Next step, I'm going to collect like terms. And so I've got 4x squared minus 12x plus 20 plus -3x squared plus -3. So that's plus, and 3 times 2 is just 6x, and then -3. Okay. Didn't need to do this step. I could have just done minus 3x squared. But let's do that here. 4x squared minus 12x plus 2 minus 3x squared plus 6x minus 3. Okay. So now I'm going to collect like terms. Collect like terms, which means that I've got 4x squared minus 3x squared. I've got minus 12x plus 6x. And then I've got plus 20 minus 3. So first thing I'm going to do, because we're just kind of starting this, I'm going to shuffle these things so that they're next to each other, which you don't have to do. If you just want to collect like terms and go for it, that's great. So one thing to note is that I will always try to write my polynomials so that the degrees are just increased. So I've got my highest power first, and then my next highest power, and then my next highest power. So I've got these decreasing powers. So I've got 4x squared minus 3x squared, and I can throw little brackets around there, it doesn't matter, because I'm not multiplying, it doesn't matter. And then I've got negative 12x plus 6x plus 20 minus 3. So this becomes 4 minus 3x squared. So what I'm doing technically is I'm pulling out this common x squared, right? Pulling it outside, and then I'm left with 4 minus 3 times x squared. But what you can do, once you've collected these like terms, then you can just look at the coefficients and say how they would behave. So 4 minus 3 is 1. So then I'm just left with x squared plus negative 12x plus 6x. Same thing, I'm pulling out a common x and then just dealing with the coefficients. But if you just want to read it as negative 12x plus 6x, then you know you've got negative 6x plus 20 minus 3. That's fine, 17. So this doesn't there. So I end up with x squared minus 6x plus 17. Good. And now I have found the difference and simplified. So now I've got this new polynomial. Okay. So we already saw the distributive property here, right, when we multiplied our 4 inside. What if we had an algebraic, so this here is an algebraic expression. What if I had another algebraic expression here that leads me to FOIL, right, which a lot of people are familiar with, probably. But we'll just do a quick refresher. For me, oops. Come on. Delete that. Okay, should be good to go. Okay. For me, the first, outside, inside, last doesn't help me at all. So if it helps you, then that's great. If not, that's okay. So it's got the little acronym FOIL, right? But essentially what we've got is if we're taking the product of polynomials, so here we're just talking about binomials, meaning, so poly means multiple, right? And then bi means two. So the nomials are just the terms, the number of terms. So here up above here, we have 1, 2, 3 terms, right? It's however many lumps we have in our polynomial. In this case, if we want to specify, we have a trinomial, right? 1, 2, 3 trinomial. Okay? So if we want to talk about a binomial, then we've got 2 terms. So here we're just going to start talking about the product of 2 binomials, but it doesn't matter. We'll extend this to just any polynomials, right? So the idea stays the same. So what you want to do is you want to multiply this A onto both the C and the D, but then you move on to B. B has to multiply C as well as the D, right? And there are a couple of ways that we could show it, right? Or go about it. We could say, okay, well, A plus B times C plus D, I could distribute that A times C plus D plus B times C plus D. And either way, you're going to end up with something like this. So if you do this kind of the FOIL, I guess first, outside, inside, last, I don't know. Like I said, if FOIL works for you, then that's great. But at the end of the day, all I need you to remember is that you need to bring each term onto the other term, right? And then follow it with the second term and potentially the third term, fourth term, however many terms you've got. So let's see here. We'll do a quick example. Good. Let's do 30. Ooh. So if I've got 4x minus 5y times 3x minus y, okay. Whether you're using FOIL or you just remember that, okay, I need to take this times this plus this times this, and then plus this times this plus this times this. However you want to expand this out is fine by me. So for me, I need to go this times this puts me at 4x times 3x plus, I'll use a different color, 4x times negative y. Then I move on to the next one, maybe I'll use that color, plus negative 5y times 3x. Plus negative 5y times 3x. And then finally, the fourth one, plus an orange, negative 5y times negative y. Now it's just a matter of simplification, right? So if you want to use FOIL and that works, great, okay, but at the end of the day, I just need you to be able to get here, right? However, whatever makes sense for you to do that. So now I've got 4x times 3x, remembering that I've got x times x, right? So now I need to deal with these exponents, right? But x times x we should be pretty comfortable with is just x squared, right? X to the power of 1 plus 1 is x to the power of 2. And 4 times 3 is still 12. So I've got 12x squared. And then the next term, I've got 4x times negative y. So instead of adding, I'm going to be subtracting, right? Because x times negative y is negative xy. So I've got minus 4xy. Same idea with the negative 5y times 3x. So I've got negative 5 times 3 is negative 15, and then x times y, there's no simplification there. So I've got minus 15xy. And then the same idea, I've got negative 5y times negative y. So a negative times a negative makes a positive. So I've got positive 5y squared. And that's because I've got the same base, so I'm able to combine those exponents, right? Wait. So plus 5y squared. Okay. So browsing through here, right, I'm checking if there's any common or like terms, I should say, right? I've got an x squared, I've got an xy and another xy, so I'm going to be able to combine those, and then I've got a y squared just off on its own. And so here what I can do is I can combine like terms. So I get 12x squared, negative 4 minus 15, 19, so negative 19xy plus 5y squared, and then we're done. Because the whole goal was to simplify. So this is simplified. There's nothing else that we can do here. Just make a note here. Good. Okay. So let's do another example from the next little group of problems. Let's do, which one? I've got 51 here. So we just want to do what it tells us to do and then simplify. And so if we start at 51, I've got the root of x times x minus the root of x. Root of x, root of x. Sounds like rutabaga. So I can expand this and simplify, right? And that's all I want to do. So I've got root x times x. Now, a lot of the time, if I have a root, I want to have the x in front, because otherwise, so here's, I'm going to show you the two options, right? And then I'll show you how I prefer to write it. So you could have just root x, x, but what can get confusing if you, unless you put a little, and even sometimes if you do put a little lip on here, just to indicate that, hey, that's the end of the root, and then this one's outside the root, for me, it just is easier to read. And so often I'll just switch it, and instead of writing it like this, I'll write it like x root x, just to show that, okay, I've got x times root x, and then there's no question about what's in the square root and what's not. It depends on kind of the flow of what I'm doing, but for the most part, that's how I like to write it. So if I've got a root, I'll put everything in front and then just the root. And then I've got minus root x times root x. X root x, well, yeah, I could probably do something with that. For example, I could have x to the 1 times x to the 1/2. Technically the same thing, just using our exponents, right? Root x times root x is x to the 1/2 times x to the 1/2. If you just wanted to skip to just x, that's fine. But I'm just showing you why. So I've got x to the 1 plus 1/2 minus x to the 1/2 plus 1/2. So x to the 3/2. Skipped some steps here, right? What am I doing? I'm adding fractions. So I need to have a common denominator. Okay, actually, you know what? I shouldn't do that. Not yet. I will be later. But for now, I've got 1, oops, 1, and then just to show what I'm doing, times 2/2 plus 1/2. And then over here, x to the 1/2 plus 1/2, that's a common denominator. And so 1 plus 1 is 2, 2/2 is just 1, so I'm just gonna write it as x. But here I've got 1 times 2/2, so now I've got 2/2 plus 1/2. 2 plus 1 is 3 over the common denominator of 2, so I've got x to the 3/2 minus x. I can rewrite this as a root, right? The square root of x to the 3, because I know how these exponents behave. So I've got the square root of x to the 3 minus x, if I wanted to. Okay. Either one of these I would accept as the final answer, right? As a simplified answer. Let's do something a little bit bigger. How about we do 58? So now we don't have, well, we could boil it down to 2 binomials being multiplied, right, and still use FOIL, which is, I mean, probably the easiest way to do it. But here we go. Either way, we need to be able to tackle these things. So 58. 58 has, okay, so we've got the square root of h squared plus 1, and then plus 1. So you want to make sure that your square root ends over that first plus 1, times the square root of h squared plus 1 minus 1. Okay. Because I'm adding in here, I can't break up the square root, right? So I'm going to have to treat this as one thing, okay? And that's going to be really important. So as soon as you have adding or subtracting inside the square root, we can't break it up anymore, okay? Since we are adding inside the root, we can't split the root up. Okay. So just as a side note. Okay, so I'll rewrite it on this fresh page here. I've got the root of h squared plus 1 times the root of h squared plus 1 minus 1. So dealing with that root h squared as one thing, right, I'm going to bring it over and I'm going to multiply the first term and then the second term, and then I'm going to take the second term and multiply it by the first term and then the second term. So I get root h squared plus 1 times the root h squared plus 1. Okay, so that's the first one. And then, oh shoot, you know what? I'm going to put this on a new page, or on the new line, because it's going to be really big. So then I've got plus root h squared plus 1 times negative 1 plus 1 times the root of h squared plus 1 plus 1 times negative 1. Okay. What's nice here is that I've got the square root and then times another square root, but I've got the exact same thing inside. So we know that this can just be written as h squared plus 1, right? The root of x times the root of x is just x. This is the same thing. So this equals h squared plus 1. And I'll put brackets around it just to show that it's the first item. So then I've got plus the root of h squared plus 1, got sloppy, times negative 1, so I guess I should write minus the root of h squared plus 1. And then I've got plus the root of h squared plus 1. And then minus 1. Okay. These two things are going to cancel, right? Negative root x plus negative root x, whatever's inside, if it's the same thing, then it just goes to 0, right? So now I've got h squared plus 1 minus 1. Well, that's also going to cancel. Womp womp. All I've got is h squared. And that's okay. That's correct. Let's do another example. We'll do 60 as an example. Right? Nice and big. Yeah, we'll do 60, but then maybe we should do 61 as well, just because. So 60, I've got it over here, is x plus 2 plus x squared times x minus 2 plus x squared. Actually, no, so I'm going to expand this, and then it'll end up being very similar to 61, so we won't have to do 61 or 62. We can just do this one. Good. Okay, so what I'm going to do is, because I'm just adding and have these brackets around here, these brackets aren't actually doing anything except for the negative has to get brought inside on the second polynomial. So what I've got is, I've got x plus 2 plus x squared times x minus 2 minus x squared, right? Being really careful about bringing that negative onto both of the terms. Now, I could spend time and rearrange these and write x squared plus x plus 2, right? Where it's decreasing in powers. I'm not going to do that until the very end, right? Because it doesn't actually matter. Same thing here, I would rewrite it as negative x squared plus x minus 2. Right? But I'm just going to hold off on that, as much as it hurts, until the end. So same idea, right? I'm going from x times x plus x times negative 2 plus x times negative x squared, then on to the second term, 2 times x, so plus 2 times negative 2 plus 2 times negative x squared onto the third term, and you just keep going and going, and you work methodically through each of the terms. So we've got, I'm going to start just skipping to x squared, right? X times x is x squared, and then x times negative 2 puts me at negative 2x, and then x times negative x squared puts me at negative x to the 3. All right, just be careful. 2 times x, so plus 2x minus 4 minus 2x squared. Now I'm on to the next term, right? X squared. So plus x to the 3 minus 2x squared minus x to the 4th. Okay. And you can use brackets if you want, but usually I'll just kind of put it all out there. It's really annoying if I miss a term, so that's why you want to just work methodically and try to work through it slowly, right? You don't want to rush through these things because they do expand really large and then they'll shrink back up. Okay. So what I'm going to do is I'm going to rearrange this. I'm going to rearrange this with, so my highest power is to the power of 4. It's going to be negative x to the power of 4, but that's totally fine. So I'm going to rewrite this as negative x to the 4. That's the only one that I've dealt with. Now what I like to do is I just like to kind of cross them off as I go, just to make sure that I've got all these terms. My next highest power would be to the power of 3, which is negative x to the 3 plus x to the 3. So what I'm going to do is I'm going to do, so plus negative x to the 3 plus x to the 3. Okay. I've dealt with this, I've dealt with that. Now I'm moving on to my next highest power. You can cancel those out, but I'm just showing that they're still there, and then in the next step I'll just make them 0, right? Which is totally fine. But when I'm dealing with something large like this, I want to go from here and show that they're still there and kind of accounted for, but totally fine if you just went to 0. Good. So now my x to the power of 2, so plus my first one is x squared, and then I scan here minus 2x squared minus 2x squared. So I've got this one taken care of, this one taken care of, and this one taken care of. Moving on to my next power, which is the x's. So then I've got plus negative 2x plus 2x. And again, same scenario. You could just cancel those out. But I just want to show that they're still there for now. Negative 2x plus 2x. And then I just want to scan here. I've only got the minus 4. And to make myself a little bit more room, I'm just going to scoot these over. Oh. Be more careful about what I'm scooting. Whee. Minus 4. I'll just show that that's taken care of too. Okay. So now I'm going to simplify inside each of these. So simplify the like terms. So I've got negative x to the 4 plus 0. And like I said, if you just want to ignore that 0, just plow through it. That's great. No worries. Just want to show you where it came from. And then I've got plus x squared minus 2x squared minus 2x squared. So that's going to be 1 minus 2 minus 2x squared, right? So I've got 1 minus 2 is -1, and then minus 2 puts me at -3. So I've got -3x squared. And then I've got plus 0 again, and then minus 4. So I get -x⁴ minus 3x squared minus 4. If you wanted to, you can pull out this common negative. So here I've got a coefficient of -1. I've got a coefficient of -3 and a coefficient of -4. I can pull out that negative, and just to get comfortable with doing that, let's go ahead and do that, even though this would be simplified and fine by me. So now I'm going to pull out that common -1, but usually we just write it as negative. So now I've got negative times x⁴ plus 3x squared plus 4. Making sure that when you expand this back in, right, you get to where we started. All right, so negative x⁴ minus 3x squared minus 4. But being able to pull out that negative is going to be really useful later on, because maybe you have a negative in the denominator and then those can cancel. And then you're done with negatives. No one likes negatives, right? So sometimes it's nice to be able to pull them out and be able to cancel them out, potentially. Okay. So let's just talk about the special product formulas. I actually don't like these, so sure, you can go ahead and memorize these if you want to. I wouldn't. I would just kind of get to know these so that if you recognize something that looks like anything on the right-hand side, you know that you could simplify it by making it look like something on the left-hand side. And usually that's how we do it. For me, having a shortcut to go from the left-hand side to the right-hand side is really pointless, because I'm just going to go through and work through it anyways. So I'll show you what I mean. But the special product formulas are more useful going the other way, which we'll see on the next page. The special factoring formulas or something they're calling them, but they're all the same pretty well. So recognizing the structure, that's going to be useful, because then you know you can simplify it to something like this. So let's see here. So here we've got these special product formulas. So if A and B are any real numbers, then we've got these kind of shortcuts. Like I said, not worth memorizing, but being able to recognize these, it might pay off, right? So here, it will be useful to be able to recognize these, and rewrite them as on the left-hand side. As on the left-hand side, right? Definitely if you're simplifying. Let's show you what I mean though, because like I said, being able to go from here to here, so going from the left-hand side to the right-hand side, I don't think it's very useful, because you can just put in the work and get to here. So what I want to do is I want to show you number 5, how we would just expand it. So we've got a minus b to the power of 3. Because I'm going to need a lot of room here. A minus b to the power of 3, remember exponents, well, that's just a minus b times a minus b times a minus b. Okay. So we've already talked about how do we deal with if we've got 2 binomials, but now we've got 3 binomials, but all we do is we expand, the first 2 typically, and then we expand onto the third binomial. Or, yeah, binomial. Okay. So first thing I'm going to do is I'm going to have a times a. So a squared minus ab, right? Going a little bit faster, looking at a times negative b, that's negative ab. And then minus, so negative b times a, I'm going to rewrite it as minus ab, because then I've got this ab term that I can collect, right? So I am picking up the pace a little bit here, or I guess a lot. But we're getting there. So, and then plus negative b times negative b, so plus b squared, and then times a minus b. So I'd say probably simplify this one before I go ahead and expand it onto a minus b again. Okay. So then I have a squared minus 2ab plus b squared, plus b squared times a minus b. Notice that this here, a minus b squared, is one of these special products, right? A minus b squared is a squared minus 2ab plus b squared. Right? So we can just do it. Now I can expand this on, so I've got a squared times a is a to the 3 times a squared minus b, so minus a squared b. Moving on to the minus 2ab and distributing that, so negative 2ab times a is negative 2a squared b. Negative 2ab minus times negative b is plus 2ab squared. And then b squared times a, so plus ab squared minus b to the 3. Really picking up the pace because I'm in my last minute here. So collecting like terms, right? I've got a squared b, ab squared, so I can collect these and say I've got a to the 3 minus 3a squared b plus 3ab squared minus b to the 3. And that's exactly what we had up here. Nice. So like I said, going from the left-hand side to the right-hand side, not that bad. I mean, you need to kind of keep your wits about you, but it's probably easier than memorizing that this is supposed to look like this. All right. Any questions? I know I'm way out of, or I'm just out of time, I guess. I'll keep an eye on the chat, but I think I'm going to stop the recording. And if there are no questions, I'm going to boot you.